Alright, so we'll begin at the beginning here. So this is lecture 1 on set theory, and so I'm just going to take a few minutes to introduce the basic terms and prove a few things. First of all, a set is a collection of elements, and we'll write x is an element of S to mean x is an element of S, but this is a funny epsilon symbol there. Alright, so here's some common examples for us. First of all, the empty set, which is a set containing no elements. We could talk about a set containing just one element. See, squiggle bracket, x, squiggle bracket, that's a set just containing the element x. It's called a singleton. We've got the natural numbers, which for us will start at 1. You can also use z plus for that. We have the integers, which is the natural numbers and their negatives as well as 0. We have the natural numbers from 1 to n. Sorry, I don't have any white out at the moment. We have rational numbers. So these are formed by fractions of integers where the denominator is non-zero. We have real numbers. All right, we'll spend a lot of time looking at real numbers in this course, of course. We have, what else do we have? We have complex numbers. All right, so we use those sometimes. A plus IB, where A and B are real, and I squared is minus 1. We have non-negative integers. So that's natural numbers, also 0. And then we have some what are called intervals. So intervals are, you should have familiarity with these from calculus already. Closed interval, open interval. This is the ray from A to infinity with A included, from A to infinity with A excluded, and you can also define similarly the other rays to minus infinity, as well as the so-called clopin and opposed sets. They're just silly terms. So anyway, these are the major players in the game. So let me get right into it. So next up, we have to talk about subsets. So a subset, what does it mean to have one set as a subset of another? A and B are sets. A is a subset of B, and we write A like that of B if and only if X is an element of A implies X is an element of B. All right. If we also have if A is a subset of B and A is not equal to B, then we'll write A as a subset with a not equal sign there, and say A is a proper subset of B. When two sets have the, what do I mean by equals, by the way? Two sets have the same elements, then we say they're equal. So A equals B, if and only if X is an element of A, if and only if X is an element of B. So you could draw a picture. Basically, the picture is something like this. If this is, let's say, B, then if A is a subset of B, you can draw A somewhere in here, right? So if I pick X in A, then X must also be inside B, right? If the picture was more like this, right? If this was A and this was B, and you could even find a single X in A which was not in B, then A would not be a subset of B, right? Oh, by the way, in this context, B is called a superset of A. All right, so an example. Even and odd integers. Even integers multiples of 2. Odd integers are multiples of 2 plus 1, all right? Both 2z and 1 plus 2z, both the even and odd integers, are subsets of the integers. And here's the proof of it, if you will. Let z be an even integer. Then z is equal to 2x for some x and z. But notice 2x is an integer, right? So that means that z in 2z implies that z is in z, which is all we need to show that even integers is a subset of the integers. All right, so, this is an example of the kind of proof we do in here. We try to use the definition to establish the logic, right? The definition here just says you pick an element in the subset and show that it has to be in the superset, right? There's the proof that the odd integers are a subset. Pick an odd integer. Notice that the 2x plus 1 is again an integer, which means that if z is an odd integer, it's also an integer. I mean, this is kind of stupid, but there it is. What's perhaps more interesting is just take a second to appreciate how these other examples nest together. Like, for example, we have empty set, subset of the numbers from 1 to n, which is a subset of the natural numbers, which is a subset of the non-negative integers, which is a subset of the integers, which is a subset of the rational numbers, which is a subset of the real numbers, which is the subset of the complex numbers in our thinking. In fact, all of these are proper inclusions because there's no equality of sets anywhere in here. Another example, we have the open interval is a subset of this half closed, half open interval, which is a subset excuse me, of the closed interval, and which is a subset of the closed interval from 0 to infinity to r again, right? So just an example. On the other hand, notice that it's also possible to have sets which are not subsets of either way, right? Like this is not a subset of that, and that's not a subset of this. So it's not necessary when we're comparing two sets that either be a subset of the other. Just saying. So, excuse me. One of the things we like to use in proofs, one of the common things that we need for proofs is a way to prove two sets are equal. And one often convenient way to do that is to show double containment. So for sets A and B are equal if and only if you can show A is a subset of B and that B is a subset of A. So this is called double containment. And the proof is pretty simple. Here it is. So suppose A and B are equal, then x is an element of A if and only if x is an element of B. So x is an element of A implies x is an element of B, and x is an element of B implies x is an element of A, because it goes both ways here, right? So this implication for arbitrary x shows me that, right? And this implication right here is what I need to prove that. So I have both A is a subset of B and B is a subset of A. So that's the forward. So when we see if and only if, we can also express that as this biconditional, right? And biconditionals, to prove a biconditional, we need to be able to prove the forward direction as well as the converse direction of the biconditional. So this is the proof of the forward direction. We're assuming A equals B, and we're proving that both of these things happen. Now, conversely, the other way around, we suppose this and this is true. A is a subset of B, B is a subset of A, right? So if x is an element of A, then since A is a subset of B, we have x as an element of B. Likewise, if x is an element of B, then since B is a subset of A, we have x as an element of A. Therefore, for each x, we have x as an element of A, if and only if x is an element of B, and thus by definition of set equality, A equals B, right? So there you go. So when proving something which seems obvious, it's especially important to convince your audience, namely me, that you understand the definitions in use and how they fit together into the logic of the proof. Sometimes just writing the relevant definition is in fact half of the proof. So let's see here what's up next. So one other fun thing we can do with subsets is we can look at the set of all subsets. This is known as the power set. Now, that's not the main point of this lecture, but it's just I'm trying to introduce all the major, kind of simple, relatively simple here set theory constructions, and this is a pretty important one for the discussion this semester, at least early on. It won't be later in the course probably, but at the moment it is. If x is a set, then P of x, that is the power set of x, it's the set of all subsets of x. And again, we call that the power set. So just to give you a specific example or two, if we have the set containing the numbers 1 and 2, then the power set is the empty set, the singleton containing 1, the singleton containing 2, and the whole set again. So the empty set is always the element of the power set because that the empty set is a subset of any set. And you're always going to see the whole set in there because we always have that, like, so what I'm trying to say is generically, it's always the case that the empty set is a subset of X, and it's always the case that X is a subset of X. By the way, I'm using this thing n equals to for subset. Your book just uses this alone. But it's ingrained, it's built into me at this point to write subset as this, because I just like that notation. It indicates the possibility of equality, and I prefer this notation, so I'm going to use it. I hope that doesn't cause any confusion. And here's with three elements: A, B, C. The power set of Y would be this, this, and that. So in this case, the sets, let's see here. I feel like I forgot to say it, but oh yes, it's a proper subset if it's not the whole set, right? So every set here, which is not the whole set, is a proper subset. So I believe there are 1, 2, 3, 4, 5, 6, 7 proper subsets of the power set of Y. There are 3 proper subsets of the power set of X. Sometimes people want non-trivial, non-empty proper subsets. Non-empty proper subsets, there's 2 of them here, there's 6 of them there. Anyway, I have a question, maybe a kind of fun question. Can you see any pattern to the number of subsets in the power set? That's something we'll come back to as we talk about cardinality. All right, moving on. So, set operations. What operations can we do with a set to understand them, to analyze them, to construct new sets, right? So, 2 big ones, of course, are the union and the intersection. Union of 2 sets is just the collection of X such that X is in A or X is in B. The intersection is the elements such that X is in A and X is in B, right? There's more. We also have set difference, A minus B. Now your textbook uses A slash B, but I'm going to use A minus B. It's just, again, I'm kind of stuck on that notation for myself, and I can't. If I try to do this, it won't go well. So I use that for set difference. And simply speaking, that just means X is in A, but X is not in B. That's set difference. And then there's also this so-called symmetric difference. The symmetric difference is the union of A not in B, A with everything in B taken away, and B with everything in A taken away. It's the symmetric difference. Also, I should mention, if we have a universal set, a set which kind of contains all the other sets of interest, sometimes called the universe, and if you have a subset of that universe, then you can talk about the complement. And the complement, A upper C, or I'll use A bar for complement, is X minus A. Now, again, your book is using A upper C, and some other people do for the complement. You can if you want, but I'm going to use bar for complement because it's a notation I'm sort of hardwired for at this point. So here's some pictures. Here's some pictures of these various operations: the union, the intersection, the difference, the symmetric difference. And so as I look at these 4 pictures, one thing that kind of sticks out to me is, like, if I took this one and I took that one and I put them together, I get that, right? So that suggests to me the following conjecture. A union B is the symmetric difference union with the intersection, for what it's worth. So I'll probably make that a homework problem for you guys to prove that. It shouldn't be hard. What are properties of set operations? Well, here's the major ones. For A, B, and C subsets of some universal set X, you have a set union with its complement is the whole universe. The intersection of a set and its complement is the empty set. I think I forgot to say this, but if the intersection of A and B is empty, they're said to be disjoint. Let me include that right now before I forget. I'll just stick it in right here, definition. if A intersect B is empty, then A and B are disjoint. And usually we talk about disjoint subsets, so A and B will be subsets of some common universal set. But anyway, I can't fit all that in here, so I'm just going to say that. So disjoint, disjoint sets, oops. Well, all right, I tried. So, let's see what else I can say. No. See, now I'm out of frame. Let's see here. The complement of the complement is a set again. The difference of A by B is A intersect B complement. You have these distributive laws, which tell you how the intersection distributes across the union, and also how the union distributes across the intersection, just like you'd expect. And also we have what are called De Morgan's laws, which tell you how the difference of a union is the intersection of the differences. And likewise, the difference by an intersection is the union of the corresponding differences. And incidentally, F and G, when we have A as being the universal set, then these become complements. And the form of De Morgan's laws, which I first learned, were these, which is that the complement of the union is the intersection of the complements, and the complement of the intersection is the union of the complements. I personally first learned this when I had a course in digital logic design, where we did these sorts of things with a heavy emphasis on digital, like ones and zeros and such. In fact, in the world of digital logic design, the union becomes a plus and the intersection becomes multiply. So anyway, that's kind of off the beaten track for this course. Let me get back on the path here. So first of all, we should actually prove some of those things. I just claimed a bunch of properties about set operations, and a lot of what we do here is to prove things, and at the moment we mostly have pretty simple things to prove because we don't have much high-powered machinery just yet. So mathematically speaking, so we're just gonna focus on some pretty simple proofs to start with. And I'm trying to show you enough of these so that if I ask you to prove something similar, hopefully you can get a kind of an idea of how you should do it. So here I'm going to prove part B and part D, maybe one other, I can't remember, but there's parts A through G. I'll probably make some of those other remaining parts part of your homework to prove those. Anyway, here's the first one. Claim the intersection of A and A complement is empty. So when we have an equality of sets, usually I try to do like double containment, but I think in this case it turned out not to be needed. So I started trying to start by assuming that, like pointing out that the empty set was a subset of the intersection of A and A complement, but after I wrote it out and got to the next sentence, I realized, there's no need to do it like that. So here it is. If X is an element of the intersection of A and A complement, then X is an element of A and X is an element of A complement, right? That's by the definition. I mean, to be more pedantic here, I might say by the definition of intersection, all right? Okay, thus X is an A, and what? What's this mean? This means X is not an A, right? But what does that say? Can you have X in A and X not in A? Well, no. That's a contradiction. So what does that mean? That means that our original assumption that X was in the intersection was flawed. Hence, there does not exist X in the intersection of A and A complement, which is to show that there is no elements in there, which is to show that A intersect A complement is the empty set. And there you go. All right, here's a little one. Here's one that's a little bit more substantial, perhaps. This is the distributive property, one of them. So claim that A intersect B union C is A intersect B union to A intersect C. So I'm going to give a proof by double containment. I'm going to start out by trying to prove that A intersect B union C is a subset of A intersect B union A intersect C star, all right? So here's how it starts. We take X, an element of this set, all right? And then I'm going to just unwrap what that tells us. That tells us that X is in A and that X is in B union C, right? Because intersection means that it's in both of the things being intersected. But what else do we know? Well, X is in B union C, right? So that means that X is in B or X is in C. Keep in mind, this is mathematical or, right? So that's not like an either or. It means mathematical or is true when X is in B, in C, but X could also be in both, logically speaking, this kind of or. It's the mathematical or, not the either or we sometimes use in English. All right, anyway, so what we have, let's gather our thoughts. We have X is an element of A and X is an element of B, or X is an element of A and X is an element of C, right? Hence, X is an element of A intersect B, or X is an element of A intersect C. Consequently, X is an element of the union of those two intersections. And therefore, we've shown X in here implies X in there, and that's what it takes to show that that is a subset of that. I'll call that star. Now I argue the other direction. I pick X in this set, and I unravel what that means for us. If X is in this set, that means that X is an element of the intersection of A and B, or X is an element of A, the intersection of A and C, by definition of union. All right, and so then X is an element of A and X is an element of B, or X is an element of A and X is an element of C, by the definition of intersection. In fact, I've used the definition of intersection 2 times here, once for A intersect B and once for A intersect C, right? I actually like my proof of this direction more because I'm being more explicit about what I'm using in terms of definitions, right? So this is really a better, I'd say that the second half is a better proof than the first half, all right? But proving things is kind of an art, right? Like, it's possible to be correct and still not get full credit if the proof is clumsy, right? Like there's a, is there a best proof? Well, it depends on your audience, right? There's almost always room for improvement. I'm trying to show you proofs which are correct. My proofs are not always the most elegant, all right? But I hope you can learn from me. I'm sure I can learn from you. All right, so collecting my thoughts. Hence, X is an element of A, and X is an element of B, or X is an element of C, right? Because logically speaking, this sentence above means in both cases X is an element of A, right? But then X is an element of B, or X is an element of C. So if you look at that, that means X is an element of A, or X is an element of B union C, right? X being an element of B union C gives me this right here, right? Okay. So then, X is an element of A intersect B union C, because it's in here and there. And so we've shown that A intersect B union A intersect C is a subset of A intersect B union C, and I'll call that star star. So in conclusion, we've shown double containment with star and star star, because we've got that's a subset of that, and that's a subset of that. I mean, in other words, so having the containment both ways shows you that they're equal by my previous result on the previous page we looked at. So there you go. Now, the proof's okay, but there is a slightly slicker way to do this one. Sometimes you can get away with this. Sometimes it doesn't quite work out, it depends on how you can see the logic of what you're doing, but in this case I see it. So I'll go through it. This is an alternative proof for D. Who knows, you guys might like this one more. All right, here we go. And this is the kind of proof you would not typically see in a textbook, because in textbooks we use words, right? So the kind of proof I just showed you in the previous page was mostly words with a few connecting symbols. This is mostly connecting symbols and just a few words. So you wouldn't typically see this in print, but sometimes this is a reasonable means of communication of a technical proof in a course like this. So I'll show you. Here it goes. But there almost always have to be sentences to complete thoughts in this course, right? Like a lot of it's, you know, writing proofs in complete sentences is something we'd like to aim for. All right, here we go. X is an element of A intersect B union C. If is logically equivalent to X is an element of A and X is an element of B union C, right? And that is logically equivalent to X is an element of A and X is an element of B, or X is an element of C. And that is logically equivalent to X is an element of A and X is an element of B, or X is an element of A and X is an element of C. And that is logically equivalent to X is an element of the intersection of A and B, or X is an element of the intersection of A and C. And that is logically equivalent to X is an element of the union of this and that, since X is either in this or in that. And I just said either or, but I really just mean or. All right. Either or technically excludes the possibility that it's in both, and I can't exclude that possibility. All right, so what have I shown? I've shown that X is in here is logically equivalent to X being in there, but X was arbitrary. So what we have shown is that these two sets are equal as they have the same element, right? So, and so I suppose technically I'm probably missing at least 2 words at the start of this, which is for every X. Maybe I should say for every X. And then this. All right. Okay. So there you go. Another proof of part H, and this one I'll do by double containment. The difference of A by B is the intersection of A with B complement. So here we go. X is an element of A minus B. Then X is an element of A, and X is not an element of B by definition of A minus B, right? But then X not an element of B implies that X is an element of the complement of B by the definition of complement. Okay? So what do we have? We have X is an element of A and X is an element of B complement, which means that X is an element of the intersection of A and B complement. So I've shown that X in here implies X in there, which means that I've shown that A minus B is a subset of A intersect B complement. All right, great. That's half the containment. Now the other direction. Let X be an element of A intersect B complement. Then X is an element of A, and X is an element of B complement. All right, but if X is in B complement, that means, of course, that X is not in B. Excuse me. So X is an element of A, and X is not an element of B. But by the very definition of set difference, that means X is an element of A minus B. Right? And we've shown that A intersect B complement is a subset of A minus B. So let's complete the thought. So what we've shown is that A minus B is a subset of A intersect B complement, and we've also shown that A intersect B complement is a subset of A minus B. Therefore, A minus B is equal to A intersect B complement. Again, this technique of proof is called double containment. All right? So I'm going to move on. But I hope that you can make some similar proofs of parts which I have not proved in that properties I showed you a couple pages back. So next up, we have, get together here eventually, guys, set operations for families of sets. So a family of sets is like a collection of sets, and we have some label on them called an index. In this case, I'm using I for the index. I and I is big I is the index set, little I is the index. Anyway, in such a situation, we can talk about the union over the index set, or the intersection over the index set, like this. And so the union is just all X, such that X is in something in the union. It's in at least one of the sets being unioned, right? And the intersection is the collection of all elements such that those elements are in every single one of the things being intersected. So it's just a natural extension of the union and the intersection we've already done for 2 sets. This is just for more. And in fact, this still makes sense when the set I is infinite. So these actually could be infinite unions or intersections. All right. And we're also going to write just union or just intersection when we don't feel like writing I and I, when it's clear what the index set is, right? And also, in the case that the index set is the natural numbers, often the notation, like you've seen in calculus, kind of like for Riemann sums or something, I equals 1 to infinity of union, or I equals 1 to infinity of intersection. This notation is often used, and we'll probably use it when the time is right. I have a couple of examples. Pretty much all my examples I've stolen from your text. I should probably say what that text is. If I could look it up right quick, I'll tell you. I've got it on my computer over here. I will find it eventually. I can't read anything. Oh, I don't have it open. Give me a second here, I'll find it. Goodness gracious. Well, I remember it's Introduction to Mathematical Analysis 1. It's a free text. Let's see here. 2nd edition by, and I'll mispronounce this. Oh no. I'm still learning how to scroll on my computer. You'd think I'd know by now. All right, I will not attempt. So it's Introduction to Mathematical Analysis 1. So I suppose I probably should have said this earlier in this lecture, but oh well. 2nd edition by Beatrice Lafferre and Gerardo Gerardo, same last name, Alafferriere, and Wyn Nguyen. I'm used to seeing that as a last name, but anyway, Wyn Mao, or M-A-U-N-A-M. So these 3 authors have been so kind as to pour their heart and soul into making this wonderful free text. It's 166 pages, and it has a lot of what we need. It's missing a few things here and there. That's why I'm adding a little bit. Not too much here. I'll add a little bit on Cartesian products in a minute, but mostly everything here is actually in their section 1.1, but it helps me to write it out and talk about some. I didn't really pay attention to which proofs they have in there. If I've proved something they have in there, that's just coincidental. I'll probably prove whatever I feel like, and you know. So if I accidentally prove one of their homework problems, that's just maybe an accident or something. In any event, here we go. An example, the index set being natural numbers, we can take as an example the sets going from minus j to j is h sub j. So if you look at the union, j equals 1 to infinity, you get the whole real line because you just keep going out and out and out. On the other hand, the intersection, you're just going to start, you start thinking about it. You go from minus 1 to 1, then you go from minus 2 to 2, you go from minus 3 to 3. Think about those intersections. It's always stuck on the original 1 minus 1 to 1. That's as big as it gets. And that's a subset of everything being intersected. Here's one example. Another example, this one actually has a honest to goodness infinite index set. Well, excuse me, this was also infinite index set, but this is, well, we'll talk more about this in a future lecture, but this is kind of a bigger infinity in some sense. This is a continuous index because we could take any number from 0 to 1. This is a discrete because the indices jump 1 to 2 to 3. Okay, anyway, I'm being vague at the moment. Let me go on. And we'll take a sub lambda to be minus lambda to lambda, the open sets. And so if we take the union over this index set J of minus lambda to lambda, basically lambda gets as big as 1 and as small as 0. So pretty much when you get to lambda equal to 1, that's kind of the end of the road, and that gives you the biggest thing. So everything else is a subset of that one. On the other hand, if we intersect, then the only thing that's common to all of these, because we get as close to 0 as we like, but not actually to 0, I think technically if we got to 0, I would define the open set from 0 to 0. I'd probably define that to be the empty set, but here we're getting into territory I'd like to not get into. But anyway, the intersection from minus lambda to lambda is a singleton containing 0. And incidentally, a future looking comment, what we've just observed is that the infinite union of open intervals is once more an open interval. On the other hand, this infinite intersection of open intervals actually turned out to be a closed set. So that's kind of a curiosity. So we'll save that later for our discussion of topology. What's topology? Well, you shouldn't know yet, right? Okay. So properties of set operations on families of sets. What can we say about those? Pretty much the things we said for two things just as well work for an indexed family. We've got distributive properties, so like the union and intersection play nice together in both senses. We also have these De Morgan's laws. They still make sense for intersections. Like the difference by the intersection is the union of the differences. The difference by the union is the intersection of the differences. You notice the flip-flopping of union to intersection, or intersection to union, I should say, the first one. And then, of course, these are really, like E and F are really a special case of C and D, where we're taking B to be the universe. When B is the universe, then these become complements, right? Now I do have a proof of something here. A proof of C, excuse me. So C is that. So I'm going to go for a biconditional proof, I would call this. So X is an element of B minus the intersection of A sub I means X is an element of A, and X is not an element of the intersection of A sub I. Now I make a little bit of a jump here. I say, well, that means that X is an element of B and X is not an element of A sub I for some I in I. So let's just skip ahead to the explaining for a second here. So I say, well, okay, so notice X is not an element of the intersection. Means that X must be an element of A sub I for all I is an impossibility, right? If X was an element of A sub I for all I, that would mean that X is an element of the intersection of all the A sub I's, which is contradiction to what we're given, which is X is not an element to the intersection of all the A sub I's. Okay, so what that means is if it's not true that X is an element of A sub I for all I, there's at least one I in I for which X is not an element of A sub I. And that's the step that I made right up here. All right, so next, if that's the case, that means that X is an element of B minus A sub I for some I, right? But that is logically equivalent to say X is an element of the union of B minus A sub I over I. It just has to be in one, and then it's in the union. And therefore, X is an element, therefore B minus the intersection is equal to the union of the differences, because I've just shown that every element of here is also in here and vice versa, right? In other words, I've actually shown double containment. They have the same elements. So there's proof. I'll leave the other parts for your homework, but I will give you this rather large hint, which is that E and F pretty much automatically follow from parts C and D with like a sentence of writing. Remember, these are the complements with respect to the universe, whereas these are differences with respect to B. So if we put B equal to the universe, the universal set, then we should get a connection between C and E and D and F, I think. All right, moving on. Moving on. So here, what can we say about the Cartesian product of sets? Well, I should talk just a little bit about ordered pairs, right? So we can construct an ordered pair like this. A comma B is the set containing A, and then the set containing A and B. So if you did that, that distinguishes the role of A and B, right? So you could use that as a way to construct pairs if you wanted to. And the key thing that you would get from that, the net effect, is that in order for two pairs, ordered pairs, to be equal, you would need that the A matches the C and the B matches the D. In other words, you need them to be component-wise equal. And that's really what we're after when we construct ordered pairs, is that the order matters, right? And more generally, if we have this n tuple is equal to that n tuple, it's only going to be the case if this one matches that one matches that one, and that one matches that one, all the way down the line, right? So they have to be equal as lists, essentially, right? Ordered lists. So we also say that this is a so-called n tuple, and I'll leave the careful construction of these to a different course. We'll just assume that this paragraph makes sense in here. I hope that's not too much of a jump for you guys. Anyway, a lot of other math courses, you just say consider an ordered pair. You wouldn't even think about it, right? So I'm already kind of quibbling more than I would usually. A cross B is the set of ordered pairs such that A is taken from A and B is taken from B. This is also called the Cartesian product of A and B. All right. You can talk about the n-fold Cartesian product of A sub I, so like A1 cross A2 cross AN. And that's the set of n tuples like this, where the ith component is taken from A sub I. These don't have to be the same kind of sets. Like we take the Cartesian product of matrices and cats, and I don't know, this could be A sub n. What do you want it to be? Set of flavors of ramen noodles. I mean, I don't know, whatever. These could be really, really different things. But, okay, fine, fair enough. Usually we take them to be the same thing most often. And when we do that, when they're all equal to the same set, then we just write A to the power n for that. Like R2 is an example of this. R2 is R cross R, or R3 is R cross R cross R. That's a use of this Cartesian product. And I suppose technically I should mention that really this and that are not equal, because a typical thing in here would be like a pair of a number with a 2 vector, whereas this would be a 2 vector paired with a number. And these are, okay, those are different, but we ignore those distinctions in our typical use of mathematics, and we just say that both of these are x comma y comma z. To be more fussy, we're making use of a one-to-one correspondence between this set and that set, which is easy enough to write down. The one-to-one correspondence is just that this corresponds to that. But we'll talk more about one-to-one correspondence in like lecture 3, I think. So let me get back on track here. So these are some properties of the Cartesian product. The Cartesian product of the union is the union of the Cartesian products. The Cartesian product of the intersection is the intersection of the Cartesian products. You Cartesian product with the empty set, you get the empty set. You take the Cartesian product intersected with the Cartesian product, you get the intersection of the Cartesian product of the intersections. And on the other hand, surprisingly, if you take the Cartesian product of the union of two Cartesian products, you'll get a subset of the Cartesian product of the unions. Now, this might be like, why isn't that equal? Well, I'll show you on the next page here. It's easy enough to understand, actually. Here's a picture we could visualize, like the A, B, C. So like A cross B, we can look at as they being sort of like that rectangle, purple rectangle, and A cross C, we kind of like the orange rectangle. Let me make it bigger, though. That'll help us understand why there's equality for one and subset for the other. I'm not actually going to prove these, but I could, if you're curious. Hey, wait a minute! I should just make those homework. Then I'll get to look at your proofs. Woo-hoo. Okay, so I might be joking. I have to actually write your homework out and decide and make sure I don't give you too much. I also need to make sure I don't give you too little either. It's a Goldilocks problem, right? You know the story of Goldilocks and the Three Bears. It's the same problem for homework. I've not asked my wife if you have Goldilocks and the Three Bears in Chinese storytelling. So a lot of these idioms and such transfer over, a surprising number, but not all. Anyway, so if we look at this, A cross B would be like this, C cross D would be like that, and so when you look at the union of these two guys, it's strictly smaller than, say, if you look at A union C cross B union D. That's this whole like gray area. So there's these two regions which are not present in that union, which are present in this Cartesian product. So that's why this in gray is larger than that in brown. Now the other thing is kind of stupid in this. B intersect D is empty, and A cross B intersects C cross D. In other words, the intersection of this guy and the brown one, that's also empty. So like the other identity is kind of stupidly true in this picture. So let me look at the picture for the other one. So here I've got A, I've got C, I've got B, I've got D. So the intersection of A and C is actually kind of like right here. And the intersection of B and D would be like there. And this is just one possible scenario, right? This is just a plausibility picture. It's not a proof, because there's a lot of different cases which are not present in my picture. Like it could be that these two, well, it could be like the previous one up that I had drawn where they're disjoint, or they could be. And there's other logical possibilities for the picture that are not covered here. Is all I'm trying to say. So this is not a proof. But it is at least a plausibility argument, right? So as you look at this, the Cartesian product of the intersections is that little gray square, right? But also the intersection of the larger Cartesian products, namely A cross B, the dotted one, and C cross D, the solid one, you know, that's also the same little square, which goes to show you that, you know, this is equal to that. All right, so I hope that's a good start into the set theory. Next time we'll turn the topic over to what are called relations, and we'll look at relations and equivalence relations. And so I look forward to that, lecture 2. This is the end of lecture 1, so thanks.